In this class, we can see how we can decode the BCH code. So this decoding of BCH code in this it is again use the syndrome decoding. So we can see how we can decode the BCH coding using the syndrome decoding. So suppose that a code word v of x equal to v0 plus v1x plus v2x square up to vn minus 1 x raised to n minus 1 is transmitted, and the transmission error result in the following received vector. So we transmitted a vector and we received another vector, that is r0 plus r1x plus r2x square plus up to rn minus 1 x raised to n minus 1. Then we are assigning that e of x be the error pattern. Then we know that the received vector is the correct code word plus that error. Then as usual, the first step of decoding a code is to compute the syndrome from the received vector r of x. Here also we are using to find the error we are using the syndrome vector. So we can see that for t error correcting primitive BCH code we need 2t amount of syndrome. That means if we need to correct 2 errors, then we need 4 syndromes. So we can write the syndrome as S1, S2 up to S2t. So 2t amount of syndrome we needed for t error correction. So we can write it as R into H transpose. Then we find that the ith component of the syndrome, for example Si is equal to R of alpha raised to I. Then this R0 plus, then we are finding this alpha raised to R of alpha raised to I is R0 plus R1 alpha raised to I plus R2 alpha raised to 2I plus up to Rn minus 1 alpha raised to n minus 1 I. So this Is belongs to 1 less than or equal to I less than or equal to 2t. Note that the syndrome components are elements in the field of Hallows field of 2 raised to m. These components can be computed from R of x as follows. Dividing R of x by the minimal polynomial phi a of x of alpha raised to I, we obtain R of x equal to a of x into phi a of x plus b I of x. So what we are doing is we are dividing, we are finding the component of components are finding using this R of x, dividing this R of x by the minimal polynomial phi a of x of alpha I. Then we are finding R of x as a of x into phi a of x plus b a of x, where b a of x is the remainder with a degree less than that of phi a of x, since phi a of alpha raised to I equal to 0. Then we have Si equal to R of alpha raised to I equal to BA alpha raised to I. Thus the syndrome component Si is obtained by evaluating BA of x with x equal to alpha raised to I. So first we are finding what is BA of x by dividing this R of x with the minimal polynomial. Then that using that remainder we are finding what is the syndrome of I. Si is obtained from BA of x, where x we are replacing with alpha raised to I. So this is the general algorithm to find this t error correcting code. So we can see one more algorithms, t error correcting decoding algorithm. We can see that. So in that we can we are finding the syndrome values as we said earlier. So after finding the syndrome, we can use this algorithm to correct this t error. So first we are find syndrome values, then from that syndrome values we are finding the error polynomial, then from that error polynomial we are finding the error location, then we are finding, after that finding the location, we are finding the error magnitude, then using that error magnitude we are going to correct the error. So we can see how we can do this. So error polynomial, we can take error polynomial e of x is equal to e0 plus e1x plus up to en minus 1 x raised to n minus 1 with at most t coefficient are non-zero. Suppose v error actually occurs. So we are taking that we can correct at most t errors. So here we are assigning that this code consists of v errors where v is less than or equal to t. Let errors occur at locations I1, I2, IV, etc. IV. Then E of xi we can write as its magnitude into its location. So ei into x raised to I1 plus ei2 into x raised to I2 plus up to eiv into x raised to IV, where ei1, ei2 up to eiv is the magnitude of errors, and this ei equal to, we can take ei equal to 1 since it is a binary code. Then I1, I2 up to IV location of error. So we have an error polynomial. In that error polynomial we can represent as its error magnitude as well as error location. So that is this representation. Then after representing like, we can find the syndrome in terms of received polynomial. So error magnitude we can write as, we've said it as error magnitude yk equal to eik for k should be 1, 2, 3, etc. And error location we said it as sk, then this sk should be equal to alpha raised to error location. We already said this error location, we are representing that this I1, I2, IV, that's the error location. So we can write from this, we can write xk equal to alpha raised to ik for xk 1, 2v, etc. that represent the error location, where xk is equal to field element associated with ik is the location of kth error. So we can relate this sk is the field element, we can relate this sk with ik, that sk is equal to alpha raised to ik. Then we can find the syndrome using this parameters like error magnitude, error location, etc. as x1 is equal to y1 x1 plus y2 x2 plus up to yv xv, and s2 is y1 x1 square plus y2 x2 square up to yv xv square, and s2t is y1 s1 2t plus y2 x2 raised to 2t up to yv xv raised to 2t. So this is the syndrome vector we can obtain. We can represent using this error vector and location. So our error locator polynomial we can represent as a of x equal to 1 plus a1x plus a2x square up to avx raised to v. Then a of x, we can factorize this a of x as 1 minus x into x1 into 1 minus x into x2 up to 1 minus x into xv. If we know coefficient of error locator polynomial a of x, we can obtain the error location x1, x2 up to xv. So first we need to find what is the error polynomial. First we need to find the syndrome vector. From that we need to find the error polynomial. Then using the error polynomial you can find the error location. Then a linear equation that relates syndrome to the coefficient of a of x can be used to find this. So we can see that what is the relation of this syndrome and this error polynomial or error location. So the coefficient of error polynomial. So first we need to find the syndrome, then we need to find the error polynomial. So to find the error polynomial, we can make the relation between syndrome and error polynomial coefficient like this matrix equation. So the matrix of first row S1, S2 up to SV, then second row S2, S3 up to SV plus 1, then the last row is SV, SV plus 1 up to S2V minus 1 into AV, AV minus 1 up to A1 is equal to minus of SV plus 1 minus SV plus 2 and up to minus S2V. So this is the relation we will get. From this relation we will get the error polynomial. So first as a trial value set V equal to T. So we are assigning that there is a T errors happen for this received vector. Then you find what is the determinant value of this matrix. First matrix S1, S2 up to SV, S2, S3 up to SV plus 1, determinant of SV up to S2V minus 1. Then if it is equal to M, we can say that this V number of errors happen for that means V equal to T number of errors happen for the received vector. If this determinant is equal to 0, then reduce V as T minus 1. Then find the determinant of S. Then repeat this step until a value of V is found, until we need a value of V in which for which this determinant of S is not equal to 0. So we need to find this determinant of S up to we have a value for this determinant other than 0. So that value of V, when this determinant of S is not equal to 0, that time what is the value of V? That indicate the actual number of errors that happen for the received vector. Next, after finding that V, we can find the error polynomial. So to find the error polynomial, we need to find the this vectors, this matrix we need to find, that is matrix AV, AV minus 1 up to A1 we need. So for that we need to move this matrix to this right side. So you will get this inverse of this into this matrix. This we can take as M. So we will get this M inverse into this matrix. So we to invert the matrix to find coefficient of A of x. To find the coefficient of A of x, then we need to after getting this coefficient of A of x, then we can solve A of x equal to 0. Then we can find x1, x2, x3, that is the error location. So after finding the error polynomial, then we can find the error location by factorizing that polynomial. So for that we can see one example. So this example, we have a binary BCH 15 by 5 triple error correcting code is there with g of x equal to x raised to 10 plus x raised to 8 plus x raised to 5 plus x raised to 4 plus x square plus x plus 1. So we can see that the question itself given that the received vector have errors at x raised to 5 plus x raised to 3, that is there are two locations we have error. So we need to prove that the two locations we have error. We need to decode that error using this BCH code. So we can see that our error polynomial is x raised to 5 plus x raised to 3, and to find this x raised to 5 plus x raised to 3, we can see that this error polynomial, the location where the errors happen. So this x raised to 3 is the fourth coefficient, that means 1 and 1, then x coefficient, then x square coefficient, then x cube coefficient. So this x cube coming at our fourth location, similarly x raised to 5 coming at sixth location. So we can see that we have two errors at location 4 and 5. So we need to decode this using the BCH code. So to decode this, first we need to find the syndrome. So you can find the syndrome using this first procedure. That means we said that if you have a g of x, then we need to divide this g of x with the received polynomial, then you will get the remainder. That remainder we need to assign that as a, if the root of bi of b1 of alpha, bi of alpha raised to I is equal to si. So that way we are finding the error S1. So here this error vector is already given, so that is x raised to 5 plus x3, x raised to 3. So we can find the syndrome directly replacing x as alpha. So you will get the syndrome as alpha raised to 5 plus alpha cube. So this question was already specified that it is a T error correcting code. So we have triple error correcting code. So for a T error correcting code, we need 2T amount of syndromes. So for a triple error correcting code, we need 6 syndromes. So first we need to find what are the 6 syndromes using this S1. So this S1 is you got it as alpha raised to 5 plus alpha cube. Next we need to simplify that alpha raised to cube plus alpha raised to 5. For that purpose we need the power representation in Galois field of 16. So for a generator polynomial, so for a primitive polynomial x raised to 4 plus x plus 1, the power of alpha and its element of Galois field of 16 we can see in that alpha raised to 5 is alpha plus alpha square and alpha cube is alpha cube itself. So we can write alpha cube plus alpha raised to 5 is alpha cube plus alpha square. So we can see that alpha raised to 5 is alpha plus alpha square, alpha cube is alpha cube. So alpha raised to 5 plus alpha cube is alpha plus alpha square plus alpha cube. So after this you can see what is alpha plus alpha square plus alpha cube. So we can see that alpha plus alpha square plus alpha cube is alpha raised to 11. So we can write syndrome vector 1 as 1 as, we can write S1 as alpha raised to 11. So this way we can find S1. Then we need to find S2. S2 is nothing but S1 whole square. So you will get it as S1 whole square is alpha raised to 5 into 2 plus alpha raised to 3 into 2. So you will get it as alpha raised to 10 plus alpha raised to 6, that is alpha raised to 7. So you replace alpha raised to 10 coefficient, then alpha raised to 6 coefficient, then same coefficient cancelled out, then on the remainder, then check that what is that resultant power, that should be alpha raised to 7. Similarly S3 is alpha raised to 5 into 3 plus alpha raised to 3 into 3. So you will get it as alpha raised to 15 plus alpha raised to 9. That's again alpha raised to 7. Then S4 is alpha into alpha raised to 5 into 4 plus alpha into 3 into 4. So you will get it as alpha raised to 14. Then S5 is this alpha raised to 5 into 5 plus alpha raised to 3 into 5. So you will get it as alpha raised to 5 after simplification. And S6 is alpha raised to 5 into alpha raised to 5 into 6 plus alpha raised to 3 into 6. So you will get it as alpha raised to 14. So alpha raised to S1 is this alpha raised to 5 plus alpha raised to 3. Then S2 is 2 times of this coefficient alpha raised to 10 into 10 plus alpha raised to 3 into 2. Then S3 is alpha raised to 5 into 3 plus alpha raised to 3 into 3. S4 is alpha raised to 5 into 4 plus alpha raised to 3 into 4. S5 is alpha raised to 5 into 5 plus alpha raised to 3 into 5. And S6 is alpha raised to 5 into 6 plus alpha raised to 3 into 6. So after simplification you will get it as alpha raised to 7, alpha raised to 7, alpha raised to 14, alpha raised to 5, alpha raised to 14, because alpha raised to 5 corresponding Galois field 16 representation is alpha plus alpha square, alpha raised to 3 is alpha raised to 3 itself, then after addition you will get it as alpha plus alpha square plus alpha raised to 3, that is the power of alpha raised to 11. Similarly, we can solve this whole syndrome. So you will get it as alpha raised to 7, alpha raised to 7, etc. So after finding the syndrome, we can find the errors, number of errors, and then we can locate the error. So first we can assign that question itself it is specified that it is a triple error correcting code. So we can set V equal to T equal to 3. Then we need to find what is our matrix M. So matrix M is S1, S2, S3. So our general formula is S1, S2 up to SV. Then this column is S1, S2 up to SV. Then the last row is S2V minus 1. So we can replace V as 3. So you will get S1, S2, S3, S2, S3, S4. Then S3, S4, S5. So that's our matrix. Then we can replace corresponding error vectors. So corresponding syndrome vectors. So you will get it as alpha raised to 11, alpha raised to 7, alpha raised to 7, alpha raised to 7, alpha raised to 7, alpha raised to 14, alpha raised to 7, alpha raised to 14, alpha raised to 5. So first we need to find the determinant. If the determinant is equal to 0, we can reduce this V as T minus 1. Then we can again find the determinant. So first we can find the determinant of this S. So this for this finding the determinant we can use the determinant equation as usual. So this alpha raised to 11 into alpha raised to 7 alpha raised to 7 into alpha raised to 5 minus alpha raised to 14 into alpha raised to 14. Here minus and plus are same because it is modulo to addition. So we can write it as alpha raised to 11 into alpha raised to 7 into alpha raised to 5 plus alpha raised to 14 into 14 plus alpha raised to 7 into alpha raised to 7 into alpha raised to 5 plus alpha raised to 7 into alpha raised to 14 plus alpha raised to 7 whole into alpha raised to 7 into alpha raised to 5 into alpha raised to 7 into alpha raised to 14. That means the normal determinant expansion, that is alpha raised to 11 into alpha raised to 12 plus alpha raised to 28 plus alpha raised to 7 into alpha raised to 12 plus alpha raised to 21 plus alpha raised to 7 into alpha raised to 21 plus alpha raised to 14. So that's our usual matrix expansion, usual determinant expansion. Then we can replace this alpha raised to 11, alpha raised to 14, alpha raised to etc. in terms of Galois field of Galois field extension, that is Galois field of 2 to Galois field of 16 extension. So we already said alpha raised to 11 we can represent in this Galois field of extension as alpha raised to 11 as what? Alpha plus alpha square plus alpha cube. Similarly, you can expand alpha raised to 14, alpha raised to 7, etc. So if it is alpha raised to 21, then we can see that if it is greater than 15, you can convert that in terms of alpha raised to 15. So for example, if it is alpha raised to 21 means it is alpha raised to 15 into alpha raised to 6 is alpha raised to 21. So that alpha raised to 15 becomes 1, so remaining is alpha raised to 6. Then you can use that expression alpha is alpha raised to 6. So you can replace. So that's the way we can this way we can expand the determinant and find the determinant value. So after finding this you will get it as here it's not given. So after finding this you just replace alpha raised to 11 its power expansion in Galois field of 16 and simplify that. In simplification we know that it is a modulo to addition, so the same coefficient cancel. For example, if it is 1 plus alpha plus 1, then it is 0 because alpha plus alpha is 0, 1 plus 1 is 0. So this way we can simplify. For example, if it is alpha plus alpha square plus alpha cube plus alpha square, then the remaining is alpha cube only. The remaining remaining terms cancel. So this way we can do the modulo 2 addition. So this is simple determinant expansion, in that we can replace this alpha raised to 11 and alpha raised to 7 terms. If it is greater than 15, you can convert that alpha to in terms of 15. For example, if it is alpha raised to 18, then you can convert it to alpha raised to 15 into alpha raised to 3, then alpha raised to 15 becomes 1, then remaining is alpha raised to 3 only. Then you can substitute alpha raised to 3. So this way we can find this solution. So after finding this, you will get that determinant is equal to 0. So we can say that there is no 3 errors in that received vector. So the errors happen in that received vector is less than 3. So make it as t equal to 2, v equal to 2. Then our matrix become s1 s2 s2 s3. Then replace s1 s2, then s2 s3. Then you can find this determinant. So it is alpha raised to 18 plus, it should be minus, but here plus and minus is same. So alpha raised to 18 plus alpha raised to 14. So what is alpha raised to 18? Alpha raised to 18 is alpha raised to 15 into alpha raised to 3. Alpha raised to 15 is 1. So alpha raised to 3 plus alpha raised to 14. So alpha raised to 3 is alpha raised to 3 itself. Then what is alpha raised to 14? We can see alpha raised to 14 is alpha raised to 3 plus 1. So alpha raised to 3 plus 1 plus alpha raised to 3 is 1. So we have determinant of m is not equal to 0. Its value is 1. So the t value for that is the number of errors. So what is the determinant of determinant of s is not equal to 0 at the time, what is the t value? That is the number of errors. So we can say that here number of errors is t is that time is 2, then the number of errors, 2 errors happen in this received vector. Then we need to find the location of the received vector. So we can write this again, we can see the general equation. So to find this, we need to find av minus 1. So it become a2 a1. So to find this, we need to take this matrix here, so that become inverse. So this inverse into this value. So we can see that is, we can write it as m inverse into s3 s4. M inverse is inverse of this matrix. So to find the inverse, we know it is adjoint of this matrix divided by determinant of this matrix. Determinant of that matrix is already 1. Then we can find the adjoint of that matrix. Adjoint is cofactor transpose. So you will get it as alpha raised to 7 alpha raised to 7 divided by alpha raised alpha raised to 7 alpha raised to 7 alpha raised to 7 alpha raised to 11 into alpha raised to 7 alpha raised to 14. So alpha raised to 7 into alpha raised to 7 plus alpha raised to 7 into alpha raised to 14. Then here alpha raised to 7 into alpha raised to 7 plus alpha raised to 11 into alpha raised to 14. So this is alpha raised to 14, and here alpha plus alpha raised to 21, and here is alpha raised to 14 plus alpha raised to 25. So this is our matrix. Then we can again replace this alpha raised to 14. What is in Galois field extension, you can replace alpha raised to 14. Alpha raised to 21 is alpha raised to 15 into alpha raised to 6. In that alpha raised to 16 we can 6 we can replace. Then again alpha raised to 14 we can replace. Alpha raised to 25 is alpha raised to 15 plus alpha raised to 15 into alpha raised to 10. In that alpha raised to 10 we can replace. So after replace, you will get it as 1 plus alpha cube plus alpha square plus alpha cube, and next row is 1 plus alpha cube plus 1 plus alpha square. So in that alpha cube cancels, that is 1 plus alpha square. Here it is 1 cancel, remaining is alpha plus alpha square plus alpha cube. This power term is equivalent to alpha raised to 8, and this is alpha raised to 11. So you will get it as a2 is alpha raised to 8 and a1 is alpha raised to 11. So our a of x we can write after getting this coefficient. You can write this polynomial, error vector locator polynomial, as 1 plus a1x plus a2x square. So you will get it as 1 plus a1x, that is 1 plus alpha raised to 11x plus alpha raised to 8x square. Then we need to factorize this polynomial. So after this we can see that the multiplication result should be 8 and addition result should be alpha raised to 11. So you will get it as 1 plus x into alpha cube into 1 plus x into alpha raised to 5. So then we can find the error location. So here we can have to find the error location. We can take this alpha as x, then you will get it as x raised to 5 plus x cube. So that is the error. So that's our question. So to check this error location, if the error location is x raised to 5 plus x cube, then we need to prove that. So we found the error location or the error polynomial is x raised to 5 plus x cube. So this is the error polynomial. So this is error locator polynomial and this is the error vector or the error polynomial. So this way we can decode the BCH code. And one more thing, we can make sure that how we can factorize this error vector polynomial. So while factorizing this error vector polynomial, we can see that alpha raised is the product of two terms and addition of that two terms give alpha raised to 11. So you select what are the different possible way to get alpha raised to 8. You first factorize this alpha raised to 8. So we can factorize this alpha raised to 8 as alpha raised to 5 and alpha raised to 3, or alpha raised to 4 into alpha raised to 4. So in that first we can factorize it as alpha raised to 5 into alpha raised to 3. Then that should be alpha raised to 5 plus alpha raised to 3 should be alpha raised to 11. For that we can see that we can replace this alpha raised to 5. So this alpha raised to 5 is alpha plus alpha square and alpha raised to 3 is alpha cube, alpha raised to 3 itself. So we will get the sum as alpha raised to 5 plus alpha raised to 3 as alpha plus alpha square plus alpha raised to 3. That is same as that of alpha raised to 11. So we can see in that field extension we can see that what is alpha raised to 5? Alpha raised to 5 is alpha plus alpha square and plus alpha cube is alpha plus alpha square plus alpha cube is alpha raised to 11. So multiplication is alpha raised to 8 and addition is alpha raised to 11. So that factors are alpha raised to 5 and alpha raised to 3. So this way we can find the factors of that error vector polynomial. So we can summarize this steps to how to find this, how to decode this BCH code. We can summarize. So the first step is that we need to find the error syndrome vector. We need to find the syndrome vector. So to find the syndrome vector, we can use the equation r of x. We can change r of x. R of x equal to syndrome. So that calculate error syndrome from r of x, that is syndrome I is equal to r of alpha raised to I. After that we can find this using this syndrome vector. We can find the number of errors. So we can make this find the number of errors. After using the syndrome, we can make the number of we can find the number of errors using the equation. Find the determinant of that syndrome. If the determinant of syndrome is equal to 0, then we can reduce the errors to first we can set v is equal to t. Then we can find the determinant of this syndrome vectors. Then if it is equal to 0, we can reduce t as t minus 1. Then we can again find the determinant. If it is not equal to 0, means that v is equal to t minus 1 is the number of errors. So after finding these errors, we can find the coefficient of error vectors using the equation determinant of av. Determinant of AV to A1 is equal to M inverse of matrix of AV to A1 is equal to M inverse of matrix M inverse into matrix minus SV plus 2 up to this equation. We can use this equation, general equation, to find the coefficient. AV up to A1 is equal to M inverse. This is M inverse into minus SV plus 1 up to minus S2V. So using that equation you will get the error vector location. So using that location you can find the error vector polynomial. So this error vector polynomial is a of x equal to 1 plus a1x plus a2 x square up to av x raised to v. And after finding this error vector polynomial, you can factorize the error vector polynomial. Then using the factors you can identify what is the error polynomial. So this way we can, by replacing alpha to x, you will get that error polynomial. So this way we can easily decode BCH codes.